This video is going to cover soaps and the soapless detergent part of the CFE Higher Chemistry course. These are the learning outcomes from the SQA we're going to cover today, and we will revisit this at the end of the video. So how are soaps made? Well, they're produced by reacting fats or oils with an alkali, typically sodium hydroxide. So if I wanted to make palm olive soap, I would have a mixture of palm oil and olive oil, and I'd mix this with sodium hydroxide. I'd probably put some other chemicals like fragrance chemicals in there to give it a nicer smell. You can make soap from lard or dripping and add that to sodium hydroxide and make tallow soap or lard soap as well. So fats or oils are reacted with an alkali to form soap. So we're going to look a bit more closely at the chemistry behind soap formation. So we can say that soaps are salts of fatty acids. The one time we've come across salts at National 5 would have been a neutralization reaction. So there is a neutralization part to the process of making soap. The whole process we use to make soap is called alkaline hydrolysis, and it's often used to make sodium salts of fatty acids. So let's take our fat or oil, and the first stage is the hydrolysis of it to form glycerol and fatty acid. So here's a typical fat here. This is one called glycerol tristearate. You can see that we've got the three ester links present in the fat. This would be the part of the glycerol molecule that was formed in the fat, and we've got our three fatty acids which are attached here. Now if we're hydrolyzing it, i.e. breaking it up using water, we're going to break up these three ester links by putting the hydrogens back onto the oxygens here and the hydroxyl groups back onto the C double bond O's here in order to get our acid groups back onto the fatty acids. So because we've got to break three ester links, we're going to add 3 molecules of water, and we're going to hydrolyze this at the break here of the ester link to form glycerol. You can see we're putting our hydrogens from the water back onto the glycerol, so we've got our 3 hydroxyl groups for our glycerol, our propane 1,2,3 triol, and we're getting 3 fatty acids produced. In this case we would call this stearic acid. And you can see we've got the carboxyl groups at the end here. Now the next slide we're going to look at one of these fatty acids because there's another stage to this process to make soap. So this is the hydrolysis step. The next stage is the neutralization of the fatty acid with sodium hydroxide. So in the first stage of soap formation, we took a fat or an oil, we hydrolyzed it with water to produce glycerol plus 3 fatty acids. We're going to look in detail at one of these fatty acids. You can see we've got a carboxylic acid group here. The reason this is an acid is because the hydrogen atom can dissociate to form a hydrogen ion. If you remember from National 5, the definition of an acid is a substance that when dissolved in water will produce a greater concentration of hydrogen ions than hydroxide ions. If the hydrogen ion dissociates, we're left with a negatively charged carboxylate ion formed. Now because this is an acid, you remember from National 5, if you react an acid with an alkali, such as sodium hydroxide, you will end up with salt plus water. So we're going to get an ionic salt being formed. In this case, we're going to have our carboxylate ion, our sodium stearate ion. That's going to be our negative ion in the ionic salt, and our positive ion will be the sodium ion. So our ionic salt is called sodium stearate. That's basically our soap, which would be a solid at room temperature. And the thing to note about the soap is that we have a charged or polar head. This part will be soluble in water, because remember, like dissolves like, polar dissolves in polar. We also have a big long hydrocarbon group, which is our non-polar part of the molecule, and this part will be soluble in oil. So to summarize, soaps are produced by the alkaline hydrolysis of edible fats and edible oils. The first part, the hydrolysis, will produce 3 fatty acid molecules and a glycerol molecule, and then the fatty acid molecules in turn are neutralized by the alkali, such as sodium hydroxide, to form water-soluble ionic salts called soaps. So let's have a little look at the soap ion. You can see that the soap ion contains a long hydrocarbon part to it. And if you think back at the bonding, whenever you see a long hydrocarbon part, that's going to tell you we've got a non-polar part overall. Like dissolves like, so this non-polar part will dissolve readily in non-polar solvents such as fat or oil. We can say this group is hydrophobic, i.e. it's water hating. We know that fats and oils don't mix with water, they don't particularly like being in the presence of water, so we say this is a hydrophobic group, if you like, a water hating group. This part of the molecule has a preference for being soluble in fats and oils. You can see this part of the molecule has got a negative charge and a positive charge, so we've got quite a polar group here. This part here will be water soluble. Remember, like dissolves like, polar dissolves in polar, so this part of the molecule will dissolve readily in water. So to summarize, soap ions have a long non-polar tail, which is readily soluble in non-polar compounds such as oil or grease. We say they're hydrophobic, and an ionic carboxylate head, which we say is hydrophilic, i.e. water liking, and this is water soluble. So soaps can be used to remove non-polar substances such as oil and grease from dishes and clothes and so on. And they do this because of these long non-polar tails, which are readily soluble in non-polar compounds, i.e. they're hydrophobic, and they also have these ionic heads, which are water soluble, i.e. hydrophilic. So the first part of the cleaning process using soaps involves the hydrophobic tails, if you like, dissolving in some grease. So imagine we've got a lump of grease in some clothing here. The long non-polar tails dissolve in the oil, and the hydrophilic heads remain in the surrounding water. And if you agitate this a little bit, this will break up the fat or oil into smaller droplets, which tend to look like this. These ball-like structures are often called micelles. And the negative charges in the hydrophilic groups will repel each other and keep the oil or grease suspended in the water as that oil is broken up. We'll look at this in a bit more detail at each stage again. So here's the cleansing action of soaps. So imagine we've got a lump of grease here, and we've got these big long non-polar oil soluble tails and these negatively charged, if you like, hydrophilic heads. So what happens is the big long hydrocarbon part is soluble in the grease. This will dissolve in the grease. On the outside of the grease, these negatively charged hydrophilic heads remain in the surrounding water. If you shake it and agitate it a little bit, this will cause these ball-like structures of grease to form. And what keeps the fat coming together again is the negative charges of the hydrophilic heads on the outside of the droplets. So there's electrical repulsion from the negative charges caused by these hydrophilic heads. This animation shows you the structure of a soap molecule with a hydrophilic water-soluble head and a hydrophobic oil-soluble tail. The animation also shows how the structure of the soap molecule allows the soap to clean grease off clothes. So you need to be able to describe how the structure allows soaps to clean oil and grease off of various substances and how they cause oil and water to mix. So here's an example of a past paper question. What I'd like you to do is pause the video, have a go and see if you can get the points shown in the marking scheme. Diagrams will help, or labeling of the molecule will help too. Okay, so you can see in this soap molecule we've got a big long non-polar part. You could circle that in an exam and label this non-polar oil soluble, and so on. And this is our charged hydrophilic head, which is polar. This is the water soluble part. In any exam, it would be fine to circle that and label that too. So now we need the description. So here's where 3 marks come from. 1 mark is to show that the compound has an ionic hydrophilic part, and you've got to say both here, a non-polar hydrophobic part as well. And you can have a diagram showing this as well. You need to correctly identify the part that dissolves in water, i.e. the charged hydrophilic head, and you need to show that the long hydrocarbon chain is hydrophobic or oil soluble. That's the 2nd mark. The 3rd mark is to talk about how agitation separates the oil from the surface or causes small oil droplets to form. Or you need to mention how the negatively charged hydrophilic heads repel each other and keep the oil or grease suspended. Or you can mention emulsions or micelles as well, which will come into emulsions in the next video. Now, in certain parts of UK, you get hard water. And this basically has water containing high levels of dissolved metal ions such as calcium and or magnesium ions. If you use soap in these kind of parts of the UK that have hard water, then you can get an insoluble white solid being formed when you use the soap, which we often call scum, which is an insoluble precipitate. And this can be found in kettles and showers, often known as limescale. So in some parts of the UK that have high levels of these ions, if you use soaps or use these type of hard water, you can get these insoluble solids called scum or limescale formed on kettles or taps. Now, instead of using soap, you can use something different that won't cause this. And this is detergents. So soapless detergents are substances are like soaps. They've got non-polar hydrophobic tails as shown here, and they also got ionic hydrophilic heads. So these remove oil and grease in the same way as soap, i.e. they have a non-polar part that dissolves in the grease, and they have negatively charged parts on the outside the grease that keeps them suspended. However, the advantage of soapless detergents is they do not form scum with hard water. So here's an example of a molecule called SDS, which has got a big long hydrophobic tail, which is soluble in oil, and a hydrophilic head, which is water soluble. So have a go at this question. Pause it and see if you get the right answer. So the question is asking you which of the following is the salt of a long chain fatty acid. Well, if we break up fat or oil using hydrolysis into fatty acids plus glycerol, then we neutralize the fatty acids with sodium hydroxide, we will end up with an ionic salt called a soap. So this is a summary of the SQA learning outcomes covered in this video. So I hope you found this video useful.